Okay, be right. Just a few seconds. For some reason it does. Okay, please go ahead, Carla.
Okay. Good afternoon, everybody. It is really an honor for me, and it's my pleasure to introduce Professor Tom Yukes. Actually, Professor Tom Yukes does not need any introduction. He is a professor of aerospace engineering and engineering mechanics at the University of Texas at Austin, and he has there the holder of the Peter O'Donnell Junior Chair in Computational and Applied Mathematics, and he also the leader of the ISIS group in computational mechanics. Before joining Austin, he was a faculty member at the University of California at Berkeley. And I would say that Professor Tom Yukes is surely one of the most reputed and eminent researchers and authors in scientific computing. His research interests include, but are not confined to, they include computational mechanics, isogeometric analysis, stabilized and variational multiscale methods, cardiovascular bioengineering, complex fluids, and turbulence. In particular, he's the founder of isogeometric analysis that he founded in, say, at least the first paper, the seminal paper is 2005. And so it is really my pleasure to attend this talk. Thank you, Tom.
Well, thank you, Carla, for that very kind introduction. Let me get right to the topics at hand. I'm going to give an overview of isogeometric analysis. I'm going to talk a little bit about how it got started, current status, some of the things that have been done recently, and I'll say a little bit about structure-preserving methods, very little in fact, but just as a segue into the class that will begin tomorrow. So this is the outline, as you can see. I'm going to say a little bit about classical finite element analysis and its comparison with isogeometric analysis. That'll give you some idea why this subject began. For the uninitiated, I'll give a brief overview of, I'd say, the main tools in isogeometric analysis, B-splines and NURBS. And then I'll talk about refinement schemes when you take these technologies to partial differential equations, in particular H and K refinement. And H refinement, of course, is the classical mesh refinement, but K is something new, and I'll describe that. It's something new from within isogeometric analysis. I'll say a little bit about functional analysis approaches to error analysis, and I'll spend some time on spectral analysis. They're very complementary technologies for proving things about methods for solving partial differential equations. Then I'll show a number of applications just to show you that this topic has gone from, let's say, its elementary beginnings to more complicated real-world applications. And then, as I said, a little bit about structure-preserving methods and some final thoughts. So the origins of IGA really began when a number of individuals were telling me about problems they were having in industry. In industry, when you do engineering analysis with finite elements, the finite element models are created from the designs. The designs are encapsulated in CAD representations, computer-aided design representations. The interesting thing about that process is it's much more complex and time-consuming than one would initially imagine. You have to fix CAD geometries to make them suitable to generate finite element models, at least traditional finite element models. And this accounts for a huge portion of overall analysis time. It's a major bottleneck in the product development process. There was a study done at Sandia National Laboratories, and there they have about 10,000 people, and most of them, I'd say, are computing. And so they do an inordinate amount of finite element analysis. So they were able to get very good statistics on the process. And they sort of confirmed that and documented that in a famous report, the DART report. But this comes from all different sources. The Navy was very influential, the US Navy, in getting me to look at this problem, because they were getting situations that were even much worse than this. In addition to create the mesh, in addition to creating the mesh model, you have to do certain things. You have to remove features. You have to heal damages, flaws in the CAD file. And in the process, you really recreate the geometry. So you wind up approximating the geometry. And that can be severe if it comes to higher order techniques. So what's the problem? Why is it so time consuming? Well, this is a simple model. This is just a part from a Honda. That's a B pillar. And it's one piece of metal. It's been cut, stamped, holes have been drilled into it. And so you would imagine it would be very simple to generate a finite element mesh for that part. Well, it's not so simple when you come to the data structure. The actual data structure consists of 1,280 so-called trimmed surfaces. Those are images of rectangular patches that intersect, and those intersections are not watertight. Mathematically, they can't be, given the underlying order of the functions that are utilized. So you have gaps and overlaps, and to produce a classical finite element mesh, the CAD file has to be rendered watertight. And so you have to fix it. And that becomes an ordeal. Imagine this one little piece consists of 1,280 images of rectangular patches. So what are the problems in total for FEA? Well, model creation, as I just indicated, geometry errors. If you have to make simplifications, you might be removing fillets, small holes, replacing fillets with sharp corners, things of this kind that can really change results. Another problem is closing the loop with design optimization. You want to automate the design optimization process, so you have a loop doing forward analysis, and then you change the design according to the outcome of that analysis. Now, in traditional FEA, once you're done with the analysis, you have left the data structure of CAD, and you have to bring the FEA results back to CAD. And sometimes that amounts to just walking down the hall and telling the designer what the changes are that need to be made. You'd like that to be completely automated. So this is a problem with FEA. I'd say the final problem, and one I'll speak to as we go along, is the promise of higher order elements in FEA has not been realized. If you look at widely used commercial and industrial finite element codes, they rely heavily on the lowest degree elements in structures, bilinear quadrilaterals and trilinear hexahedra, and in fluids, linear triangles and linear tetrahedra. So why is that? I mean, the academic literature would suggest that higher order elements are capable of higher order convergence rates, but we'll see there's a problem that is not discerned by traditional functional analysis techniques. So the objectives of FEA from the start were to fix this problem of the development of models by reconstituting finite element analysis within CAD geometry, and to simplify the model development thereby for analysis, and to integrate design and analysis. And that was the goal, the original goal. So as Carla mentioned, the first paper was published in 2005. It was me and two of my graduate students at the time, Austin Cottrell and Yuri Basilevs. And that was the beginning. If you go to Web of Science, for example, and you put the topic isogeometric in, you'll find now there are over 3,000 papers on the subject and over 72,000 citations to papers. And there were over 16,000 last year. This is still growing more or less quadratically. So it has garnered quite a bit of attention, and people are using it for all different things. So what is it? It's based on the technologies that come from computational geometry: NURBS, T-splines, U-splines, various unstructured splines, subdivision surfaces, etc. And these, as you may be aware, are used in design, animation, graphic art, visualization. Now, in fact, classical finite element analysis can be found embedded in here as a special case, but these techniques offer greater possibilities. In particular, precise and efficient geometric modeling, simplified mesh refinement strategies. You also can produce smooth basis functions with compact support. Smooth basis functions open up the possibility of solving higher order partial differential equations with very, very simple techniques. And what we found that we didn't realize early on, and as you'll see, superior approximation properties. That is a surprise and was a surprise. And of course, the integration of design and analysis procedures. So although I started my career as a designer, I became an analyst shortly thereafter. And so I sort of view isogeometric analysis primarily through the lens of analysis. And I think if one does that, one can think of it as a superset of technologies that contain traditional finite element analysis. The usual techniques for improvement: mesh refinement, H refinement, polynomial refinement, say on a fixed mesh, some linear combination of the two. But what you have as sort of the secret weapon of isogeometric analysis is K refinement, where in addition to raising the degree of, say, the underlying polynomial basis, you also increase its smoothness simultaneously. So let me begin with a tutorial on B-splines and NURBS to get everybody sort of accommodated to the basic ideas that we'll be developing here. B-splines are polynomials. They're piecewise polynomials, and they're defined on a patch, an interval, that is divided into sub-intervals that are bordered by so-called knots, xi and xi plus 1, or consecutive knots. And there's a famous Cox-de Boer recursion relationship for deriving higher order splines, starting with the piecewise constants defined on this decomposition of the patch. So you go from constants on the right-hand side to linears, and then you put linears on the right-hand side and get quadratics, etc. And if you do that for a uniform knot vector, where the knots are just spaced uniformly as you see here, you start off with the constants, you get the linear chapeau functions of finite element analysis, and then you go up to quadratics, and then it looks different than finite element analysis. You're getting functions that are becoming smoother as you go to higher order, as you can see, and they span additional knot spans. So these are quadratics. They are C1 continuous. The linears are C0 continuous, and the constants are C minus 1 continuous. And if I go to the next level to cubics, I would span 4 knot spans. They would be C2 continuous. And in all cases, the functions are pointwise positive. Again, unlike the interpolatory polynomials of finite element analysis, the Lagrange basis, for example. So here's an example of a patch going from 0 to 5. The multiplicity of the knots at the end is p plus 1. These are quadratics, and you can see the multiplicity is 3 here, p plus 1. And it's non-uniform because at this knot we have repeated it. We could put other knots in unequal spacing, but in this case we've just done this. And what you see is the C1 continuity, once I repeated the knot, drops down to C0 continuity. Each time you repeat a knot, you reduce continuity by 1. If I repeat it again here, I would split the patch into 2. So that's the idea. You have control over polynomial degree, and you have control over the continuity. And so from the design point of view, you would take this basis, this global basis, and you can make a geometrical object out of it by multiplying each basis function by coordinates. And those are the control points. So we've just done that in the plane. Each of these, let's say, xy coordinates is multiplying one of the basis functions, okay? And you can see where it's only C0 continuous, you have this kink here. Otherwise, it's smooth. Now, it's also interpolatory at the ends where the knots have multiplicity p+1, as you can see. Now, this is sort of the design point of view. And if I move a control point, I will monotonically move the object, distort the object. And that's one of the reasons that emanates, in essence, from the properties of these functions. And it's unlike classical finite element analysis, where you have interpolatory polynomials. If I move one node, I may engender oscillations all over the place. You don't want that in design for obvious reasons. Now, that's the design point of view. But there's another point of view that is equal to it. And it is a decomposition of this into elements. These are the elements in a finite element sense. They are the images of the knot intervals here. So this is 0 to 1, 0 to 1, 1 to 2, etc. It's the images under this mapping. This is exactly the same geometric object, but now we're looking at the element structure. And what we can do is, through a procedure called Bezier extraction, we can reduce the processing of this object to a sum over all the elements, in which case all the basis functions in each element are identical. They would be the Bernstein polynomials. So we really can look at the geometric objects from a finite element point of view. In fact, from a classical finite element point of view. And that, of course, is the preferred way to assemble models in isogeometric analysis. So you have this, in essence, this bijection between these viewpoints. You can refine the mesh, just as in finite element analysis. So what we've done is we've just inserted a lot more knots. And you can see the control points now are moving toward the object, because the object isn't changing. We are doing refinement embedded in the geometry, unlike finite element analysis, where you don't even know what the geometry is when you start refining. You have to go look for it in the CAD file. So now we have a finer mesh that we might need for analysis, and we can do it again and again, as you can see. And as we do that, the control points will converge toward the object. That's classical H refinement. We can also do P refinement. So we start over. This time, we don't change the element structure. We're just adding functions. And since we want the same continuity, parameterization, what we do is we repeat knots. We started off with quadratics that was C1 continuous. Now we have cubics. To make those only C1 continuous, we have to repeat each knot, as shown here. And we can do that again to our heart's content up to quartic. Okay. Now, the most commonly used CAD technology in engineering is NURBS. NURBS are non-uniform rational B-splines. These are NURBS objects. And what you can see here is perfect circles. And you can do those, you can create those explicitly from polynomials by working in a higher dimensional space. So you have here now a set of 4 quadratic arcs that are placed according to a recipe. And you project those according to this mapping that you can see visually here, which amounts to creating a rational polynomial. And you can get an explicit representation in terms of those polynomials of a circle, and in fact, all conic sections. And obviously, these are extremely important in engineering, as you can see from these objects here. You have to have perfect circles and conic sections. So how do you do that? Well, in essence, to create, let's say, a toroidal surface, you could take the construction for a circle, and then you just take a product construction, and you would have a control net like this and a mesh like this. These are quadratic C1 continuous splines. That's a perfect torus, okay, with 16 elements. Now, you could refine it. And again, you refine it in place. The geometric object is not changing. You could order elevate the basis functions. You have the same mesh, but you have many more basis functions of higher order as before. And then you can take this idea of sort of tensor product development of splines to 3 dimensions and build objects like solids. For example, this pipe elbow. So it's very neat technology, very precise, and yet you can do freeform modeling as well, as we showed with the curve. So let's talk a little bit about the analytical consequences of using these functions, which are now rational functions. Well, first of all, they have compact support. That was self-evident, I think, from the pictures. They satisfy a partition of unity. They sum to 1. They possess an affine covariance property, in which if you apply an affine transformation to the control points, that transformation is respected pointwise throughout the object. So all rigid motions, rotations, uniform stretches and shearings are exactly represented in the physical space. Now that in the isoparametric concept, which is a modeling concept appropriate to mechanics, in which case you draw an equivalence between the geometry representation and the motion of the object, that they have to be coming from essentially the same space, the same basis functions. You can then prove all patch tests are satisfied. These are sort of engineering convergence criteria, although they have been mathematized. But likewise, you can prove error estimates and Sobolev norms. And that really begins with, let's say, the serious mathematical aspect of the subject. And to do mathematical analysis of PDE techniques, PDE models in a variational setting using function-based techniques like finite elements or isogeometric analysis, you need error estimates, at least for linear PDEs. You need approximation estimates and Sobolev norms. So once you have that, you can use all the same techniques that you've used to do classical finite element analysis, convergence proofs, error estimates, etc. And so this began with a paper that we wrote in 2006, and it was the basic estimate for Sobolev norms for approximations with NURBS. And it looks somewhat like the usual one for finite element analysis. In fact, you could almost say it looks very much like it if you would absorb the geometric factors into the constant here. The geometric factors, F is the geometric mapping, they have been sort of split out here. And that shows you that there is an effect on accuracy of the parameterization. So a well-parameterized object is better for error analysis than one that is not. Rather obvious, probably. Well, this is just the a Sobolev norm of the target function. There are many things buried in the so-called constant, namely the dependence on the polynomial order, the smoothness of the functions, but they're hiding in there. But the main thing here is this is useful for classical mesh refinement, because what you have explicitly is the power of the mesh parameter. This is sort of the size of the elements. And the exponent here is the optimal estimate for these Sobolev norms, and they are exactly what you would get under the best of circumstances with classical finite element analysis. So everything at this level of mathematics looks the same. And then there were a slew of studies thereafter that have been looking at this more deeply under more general circumstances. But with this, you can prove theorems as one has been doing for years and years in classical finite element analysis. So what do they tell you? Well, they tell you the rate of convergence of a problem, say an elliptic boundary value problem, when you refine the mesh in the classical way. So we'll take a look at that. We'll take the classical, just an example, the classical solution for an infinite plate with a circular hole. And you can model a quarter of the plate. You don't model infinity. You just put the exact solution on the boundary. This is an exact circle. So these are really NURBS. This is a 2-element mesh, and it's just bisected up to mesh 6 here. So one thing to keep in mind is that despite the fact we keep changing the mesh here as we refine, the geometry map is fixed. It's exact throughout the refinement. It never changes. Unlike finite element analysis again. So that complicated expression I showed you with the gradients of the geometry map, that part is fixed in the error estimate. So this is the 2-element mesh. That's not a bad solution. This is the classical exact solution, shows a stress concentration in the axial stress right at this point of the hole. You're pulling horizontally, so you're going to get a stress concentration there, and it is independent of the size of the hole. It's always a factor of 3 times the load at infinity, so it should be 30, and you can see it's converging toward that. So this is what you would expect to see given that approximation, and indeed you see it. If you took the L2 norm of the stress as a measure, which is mathematically equivalent to the energy norm, although it's a little bit more physical because it's stress rather than energy, I would say, more physically relevant. The convergence rates you'll get are 2, 3, and 4 for quadratic, cubic, and quartic elements, respectively. And you can see those rates are optimal. So in this direction, what we're doing is we're reducing the size of the mesh. We're adding degrees of freedom. They're increasing, and so on, the usual picture. Now, this is for NURBS. If I did this for finite elements, I would see the same thing. If I plotted both sets of data on the same curve, or the same plot, and I scaled them so the degrees of freedom were equal, the finite element results would be up higher. They would be converging at the same rate, but they would be higher than these. So these are more accurate, as we will find out later. Now let me talk about K-refinement. What is K-refinement? Well, to understand K-refinement, you have to start with P-refinement. Let's start with a quadratic finite element basis. These are C0 continuous, just 3 elements. And what we're going to do is order elevate, but keep the continuity C0. All right. So we order elevate from quadratics to cubics, cubics to quartics, quartics to quintics, and you can see we're piling up the functions within each element. Okay. Now K-refinement, in some sense, is the same idea. You start with quadratics, you're going to go to cubics, quartics, and quintics, but each time you raise the order, you raise the continuity level. So you go from C0, C1, I should say, to C2, to C3, to C4. And you can also see, if you just count the functions, there are many fewer right here, even in this simple 3-element test. Now keep in mind, we have the same number of elements, so the same mesh parameter, same order of approximation, but many fewer elements, many fewer functions. So what is this? This is sort of a new technology. It occupies the space, in my mind, between low-order finite element methods and spectral methods. Okay, we never had tools like that, at least to my knowledge, we never did. So let's compare classical P refinement and K refinement. Start with a one-dimensional mesh, n basis functions of order P, and then we're going to do R refinement levels. So what are the number of basis functions? They're going to be order P plus R, same. And for P refinement, they're going to be order n times R. And for K refinement, order n plus R. Obviously, if n is big, R is maybe less, but 5, something like that, this number is going to be much bigger than this number. And it really becomes dramatic when you go to multi-dimensions. When you go to 3 dimensions, for example, if I start with a mesh with 100, let's say, control points in each direction, so 1,000,000 control points, 100 by 100 by 100, and I do 10 levels of refinement, order elevation, I would wind up with about 1.3 times 10 to the 9th control points. So starting with 1,000,000 control points, I go to 1,000,000,000 control points. Now with K refinement, I start with 1,000,000, and after I execute the same process, go through 10 refinement levels, I'm still order 1,000,000 control points. You're basically asymptotically not changing the number of degrees of freedom. That's an amazing advantage, because you're working on the same mesh with the same order of approximation. So the way to think of K refinement then is I'm sort of dropping vertically, at least asymptotically. I'm dropping vertically, keeping the mesh constant. And in doing so, even though the degrees of freedom are not proliferating as they are in P refinement, I'm picking up very large increases in accuracy. Here in just 2 levels, we go through over 3 orders of magnitude in improvement. So it's sort of a magic technology. Now, the first thing, because we're using functions that span more not spans, it kind of intuitively seems that the bandwidth must be increasing. That's not the case. That's not the case. And here's an example that just illustrates that. If I have C0 cubic finite elements, and I look at the coupling between this function and all the adjacent functions in the mesh, you can see I couple to 3 to the right and 3 to the left. And if I have smooth C2 cubic B-splines, okay, here's a function here, I have 3 to the left, 3 to the right. In both cases, the bandwidth is exactly the same. So there is not really a bandwidth increase, but the band is more densely populated. That hurts you on a direct solver, and it helps you on an iterative solver. And there have been now some studies, mathematical studies, that began to look at the K refinement process, and began with Lorenzo Barro de Vega et al. In 2012. And then I think some real breakthrough was made in the work of Bresson and Sande, who will be giving one of the lectures, giving some of the lectures in the class to follow. So let's look at K refinement versus, let's say, traditional finite element techniques, higher order finite element techniques, by way of spectral analysis. The functional analysis approach tells you something. It really is telling you something asymptotic. It's not giving you the picture of what's going on in the total mesh that you're working with. So to study this problem, we'll look at the Galerkin method for the eigenvalue problem. We'll formulate it in the usual way, usual Galerkin way, variationally. The configuration space is H1, 0 boundary conditions. This is the energy inner product, and this is the L2 inner product. So the Galerkin method is just to approximate the weighting function space and trial solution space with an expansion in terms of basis functions. And after you do that, you get a matrix eigenvalue problem that looks just like this. A classical way of generating finite element methods, for example. Now, the error analysis. The error analysis relies on the approximation result, or results like that I presented earlier. And it's really, again, the same for finite elements as it is for NURBS or B-splines. So for an order 2s differential operator, you get these results. This is the eigenvalue error. This is the eigenfunction error in the energy norm, and the eigenfunction error in L2. And you notice you have this factor h times an eigenvalue. So as you go to the higher eigenvalues, this number is getting larger and larger and larger for a symmetric positive eigenvalue problem like this. And here, for eigenvalues, you get the usual factor of 2 times p plus 1 minus s, p plus 1 minus s for the energy norm. And here in L2, it's a little bit more interesting. I won't go into that, but it says you might get some surprises for certain elements. That's true for finite elements as well as NURBs and splines. So the important point, though, is this factor in here has to be sufficiently small or you're not converging. It's got to be less than 1, obviously. And the fact is, for the higher modes in your system, it's not going to be small. So this result is telling you something about the lower part of the spectrum. Okay, they are asymptotic results. They're hiding from you information about the spectrum in its totality that's in your discrete model. And the way to investigate that issue is to look at something that I call the Pythagorean eigenvalue error theorem. And it combines those 3 error measures into one expression, and it holds for every mode in the system, every mode. So in some sense, it's not asymptotic, it's global for the case at hand. And you can use that to sort of create a budget, as you can see here. And this is for C1 continuous B-splines, quadratic B-splines. And this is the spectrum. And this is good for 100 elements, 1,000 elements, 1,000,000 elements, whatever, because small n is the mode number, big N is the total number of elements. So it's sort of an invariant spectrum after you get beyond a small mesh. So this is the eigenvalue error. This is the L2 error of the eigenfunction squared, and then the sum of the two is the energy error squared. Now this is exactly what you would expect. You get good accuracy in the low modes, and then it starts to deteriorate in the higher modes. Now what you would expect as you go to higher order, you would get better, and indeed you do. If you go to cubics, C2 cubics, you see things are pushing to the right. If I go to C3 quartics, same thing. Let me just scroll back through those and you can see the improvement each time. Now you might say, well, that's the way finite elements works. We all intuitively believe that. Well, intuition can be misleading sometimes because it's not the way finite elements work. Finite elements are bizarre. The upper part of the spectrum is really bad, as you can see here. And you get a spurious spike right in the middle of the spectrum. So the errors are enormous here. And they're enormous here. So as in the case of splines, you might hope, well, as I go to higher order, things should get better. Well, in a sense they do. They do way down here. But up here, they're getting worse. This part of the spectrum, so-called optical branch, is getting worse. And you have another spurious spike here and here. And if you keep going up, what you find is the optical branch of the spectrum diverges. It diverges. And you get these very, very unusual spikes. So if you understand this result, you may understand why higher order finite element analysis is not used for difficult problems, because any input that's in the higher modes will arouse these enormous errors. And actually, the sum of the errors here goes off the slide. That's how bad it is. And once you're in, say, a hyperbolic PDE, things will propagate. So the whole solution will be vitiated by the errors that were created in some high mode, someplace, and it goes every place. And in nonlinear analysis, it's a disaster because of coupling between low modes and high modes. So it's no wonder these techniques are not widely deployed for difficult problems. What we find here is that we get more robustness as we go to higher order. We don't have this phenomenon at all. So we'll see the consequences of that. What about cost? This is sort of interesting. This is some calculations that Giancarlo Sangalli and Mattia Tani did to show the efficiency benefits of K-refinement. So they are using fast element forms and fast matrix-free solvers to solve a problem, and they're doing it both with finite elements and with K-refinement of splines. Now these are pictures for K-refinement. You fix the mesh, and then you just order elevate, and you go from order 1 to order 10. So this is a 64 element mesh, order 1, 2, 3, up to 10, and each time you have maximum smoothness. And you can see something very interesting. Let's look at this one. As you K-refine, the cost is not increasing enormously. It is not increasing enormously. And at the same time, you're improving the accuracy by 12 orders of magnitude. 12 orders of magnitude, and the cost is, let's say, order 1. If you just take a particular case, like the 64 cubed element mesh problem, you do IGA, K-refinement over here, okay? And you do FEA, P-refinement over here. For equal, let's say, error, you can see the cost is much less. When you get down to this level of accuracy, it's about 100 times faster to do it this way than this way. 100 times, that's a big number. This is a really nice picture that I'll show from the work of Espen Sande and Carlemani and Hendrik Speliers. It summarizes the story to a degree. This is just in one dimension, but one can generalize this. This picture has a lot of information. What it's doing is it's taking various spline levels, 1, 2, 3, 4, 5, up to 10. And it is starting with discontinuous, then going to C0, C1, and upping the continuity. So if I look, first of all, at a fixed K, let's say 0 or 1, it's clear that when I fix the regularity, going to a higher order polynomial gives me better accuracy. It's more accurate if this number is smaller. Likewise, if I fix P, for example, I'm going to fix P, I'll just take this one here, which is P is 10. Each time I increase K, the continuity, I drop. So that's good. I'm getting more and more accuracy. But look where the big gain is. It's when you go to maximum smoothness. So CP minus 1, the maximally smooth spline. And that's for every case, as you can see, they all drop like a rock once they hit there. So K-refinement wants to work with the maximally smooth splines, and that's the best opportunity. And the least accuracy is for the least continuity. C minus 1, which are, let's say, discontinuous Galerkin, and C0, classical C0 finite elements. So those are functional analysis error estimates. Let's look at some applications of the technology. I mentioned things get more robust. This is a classical buckling problem that's utilized in automobile crashworthiness. You are driving a square tube into a wall. You have a perturbation at this level to initiate the buckling. And it is modeled with finite deformation plasticity, with basically a J2, so-called J2 plasticity model with linear isotropic hardening. So this was solved in LS-DYNA, and which is a commercial crash dynamics code, the major crash dynamics code in the world. And this problem had never been solved with higher order finite elements. The reason is the buckling becomes so severe, you get an accordion shape, as you'll see in a moment, that the elements, the higher order finite elements, start to turn inside out. But here we're working with, say, C3 cortex splines. The number of knot spans is 5 for one spline basis function. C0 at the edges, obviously, to get the kink in the geometry. But you can see this is a very challenging problem. Lots of contact, lots of buckling. And with classical finite elements, you just can't do this. As you go to higher order splines, you get more and more robustness. Let's look at a wind turbine problem. This problem here is one that shows the interplay with design and an analysis. It's a parametric design capability. So you build your spline model, your NURBS model, and you can parametrically change the design just by moving a slider around. This is done, this is the Grasshopper interface, a visual programming language built on the Rhinoceros CAD system. Now, once you build that geometry, you really have your analysis model. And it's a complicated geometry, all composite pieces, and they're all stacks of many layers of many materials. So you use classical laminated shell theory, thin shell theory, and you have all these different thickness distributions for the different components. So it's a complicated real-world structure. This was analyzed at Sandia National Laboratories with traditional finite element technology, sort of the type of thing that you would be inclined to use in a commercial code that works for problems like this. This is the convergence of the fundamental buckling mode. This is the error, so it's about 34% at the first mesh. And then up when you get to a mesh of about 400,000 elements, and because you have 6 degrees of freedom, essentially per element, about 2.4 million equations, you get a converged solution. In IGA, this is the design model here. This is about 8,000 elements, and it has only 3 degrees of freedom per element here because it's rotation free. So it's about 24,000 equations versus 2.4 million. You can solve this problem in a couple of minutes here. It takes a long time here. And you can see, you can refine it and you basically just sit there, but even the design model is giving you the accuracy. So you can see the potential efficiency gains in something like this. And you have this nice design through analysis procedure. I'll show you an example from Coreform. This is a flex cable made of many different layers of materials. You can see sort of a cross section here. It's very long. And this is the traditional finite element mesh that was being used with the commercial codes to solve these problems. 10 million volume elements. This is a unstructured spline mesh, a U-spline, 10,900 volume elements. And you can get about equivalent accuracy with those two models. You have 1,000 times fewer elements than the finite element case. You have about 20,000 fewer time steps, and 1,000, you compute 1,000 times faster. And you can see what you're worried about is these things buckling. So you can do these things now as parametric studies. It's impossible with with finite elements, and that's why the client here was led to adopt this approach. Let me talk about trim and immersion. Those are all body-fitted meshes. They're sort of traditional in the finite element sense. I won't go through all the individual contributors to this subject, but there are a number of them. They're mentioned here. And I won't tell you about the problems with trim and immersion, but I will say that breakthroughs have been made recently to get essentially the full accuracy of methods by computing directly in trimmed files. So this is one from Michael Breitenberger and colleagues, Kai-Uwe Bletzinger, the chair at structures at TUM. It's a CAD model. It's an oil sump. That's the nice visualization. This is the trimmed CAD file. This is the untrimmed CAD file. So what you're going to work in terms of is the trimmed CAD file. And you're going to glue the different patches together using classical, either Lagrange multiplier or Nietzsche type technology. So that'll be done in the solver. It will glue the patches together along the trim lines. That's not a good mesh for analysis. Too many little elements and big elements. So you want to uniformize it somehow. And you do that, and all that refinement is in the exact geometry. You never left the geometry. And if you compare results against an Astran calculation with many more degrees of freedom, there's no exact solution for this, obviously, but you can see the quality seems to be much better than the quality here. And the main point, though, is you have done your analysis within the CAD file. So if you want to do shape change, they're already recorded in your CAD file. You're done. So you've closed the design through analysis loop, which is very important for productivity. Now, immersed methods. Suppose you have a pristine surface mesh through a, let's say, an unstructured watertight T-spline, for example. That's what this is. So this is really a solid object, and it's still an ordeal to calculate, generate a solid mesh from something like this. What can you do? Well, you can use trim in the volumetric sense by dropping the surface model, the surface CAD model, into a box of B-splines, throw away the elements that don't intersect the actual design, do hierarchical adaptive refinement. This is an octree-based quadrature refinement scheme for the element forms, and you can solve the problem virtually automatically. And now that started with a nice B-spline, nice T-spline surface. Here's where you have a surface that is a nightmare. This object, which was generated, I guess, by topology optimization, and a CAD surface representation was made. It had 3,300 roughly gaps and overlaps of edges before it was given to healing software that is used for pre-processing finite element meshes. But there's still 250 thereafter, and there's some changes to the geometry. So I mean, it's impossible, I would say, to generate a decent solid mesh for this problem. But again, you can just drop it into a box of B-splines, and you can solve the problem even without any mesh healing. You can take the flawed file. Now, this is work of Ernst Franck's group, and Ernst really, he and Alexander Dusta made the breakthrough in showing that if you get the accuracy with approaches like this, the good accuracy that in prior years one thought was impossible within trim and immersed techniques. So this is the way of really instantiating the isogeometric concept. You just use the CAD file and you do your analysis. So the final example I'll show you involves heart valves. It's a combination of immerse and boundary fitted. In fact, it's an AL mesh for the fluid domain here that is moving with the wall of an artery. The artery wall is a solid, a hyperelastic solid, nonlinear. Everything is fully nonlinear. This is a variational multiscale Navier-Stokes solver. And you have the aortic valve in this patient-specific aorta, opening and closing through the fluid, as you can see. The valve is in the Lagrangian description. The wall, the artery wall, is in the Lagrangian description. The fluid is in the arbitrary Lagrangian Eulerian description. The mesh is moving, and the valve is opening and closing immersed in the fluid mesh. So it's a combination of immersed and boundary fitted technologies. And there seems to be now a trend going where this may be the paradigm of the future, combining boundary fitted and immersed techniques in analysis. So let me say a few words about the course that begins in earnest tomorrow, structure preserving methods, finite element exterior calculus, and isogeometric generalizations. I can't say much, I don't have much time, but I will say I know these two young gentlemen quite well, and they are really outstanding, so I think it's going to be a great course. Let me give you kind of a peek at some of the kinds of things you're going to see. This is an exact sequence. This is called the Hilbert Complex. And it is an exact sequence relating scalar potentials, vector potentials, flow velocities, and flow pressures. So it pertains to fluid mechanics. These ideas of structure preserving discretizations are extremely important in many areas, but in particular, say, in electromagnetics and also in fluid dynamics, incompressible fluid dynamics. So the idea of an exact sequence is the constants are the kernel of the gradient. This is H1. The gradient, of course, in this case, is the kernel of the curl operator, and the curl is the kernel of the divergence. And these are onto, and the divergence is onto L2. In other words, every function in L2 of pressure comes from a divergence of a flow velocity. So this is the exact sequence. Now, what you want in a numerical technology is to replicate those properties. You want to create a discrete exact sequence, and such that, at least for fluid applications, this part of the diagram commutes. Okay. If you do that, you'll automatically have the stability of the approximation for a mixed problem like a Stokes flow, where you have pressure and velocity assumptions. What's more, the weak incompressibility that is part of the mixed formulation, the saddle point problem, becomes pointwise incompressibility. You actually get exact incompressibility pointwise. You can see that's a great value in fluid mechanics, in Stokes flow, for example. And it's very simple to construct these velocities in the parametric space with B-splines. So your scalar potential is just, say, splines, tensor products of order P1, P2, and P3 in the three directions, continuity levels, alpha 1, alpha 2, alpha 3. Then you can get your vector potential and your flow velocities by these representations here. The vector potential is you're just essentially lowering the polynomial order and the continuity simultaneously in X for the X component, in Y for the Y component, and Z for the Z component. These would give rise to so-called edge functions. And for flow velocities, what you do is you sort of do the obverse here. You leave, let's say, the one component alone for X, and then you reduce the 2 and the 3. And for 2, you reduce the 1 and the 3, and so on. And that gives you velocity fields. And then for the pressures, you just reduce everything. And so you can do that in the parametric coordinates. And then you have to transform these functions to the model space, physical space. So vector potentials are mapped by curl preserving transforms, flow velocities mapped by divergence preserving transforms. That amounts to the Piola transform for flow velocities, and then pressures by just integral transform. So what's the upshot of all that? Why do you want to do things in this way and do these funny mappings? Why not just, you know, assume polynomials and stick with that as you do for other things? Well, you want to preserve features of various equations. And as an example, again, for, say, the unsteady Navier-Stokes equations written here that are governing incompressible flows, the geometric structure of the solution depends on really satisfying this condition exactly. So if you can satisfy it exactly with your discretizations, then you will get pointwise divergence free velocity field, a post-Prost vorticity vector that is also divergence free, and all of the conservation laws and growth decay inequalities that are inherent in the exact theory of the Navier-Stokes equations, all of those integral balance laws and growth decay inequalities, growth decay equalities, I should say, are possessed by the discrete solution. So linear momentum is preserved, angular momentum, energy, vorticity, entropy, helicity, everything that you would like to preserve, you get it exactly. You never get this if you don't have this type of a formulation. So this gives you a much more faithful approximation for very complex nonlinear processes. So I'll just show you something in 2D. I do have a number of examples in 3D as well, but I'll show you something in 2D because it's hierarchically refined div conforming B-splines. And in 2D, what those representations boil down to is essentially smooth generalizations of Rabillard-Thomas finite elements. You know, Rabillard-Thomas finite elements are a discretization of the H div space. The velocity field is a discretization of H div. It's not a discretization of H1 because the tangential velocities are discontinuous. But in this case, you have smoothness and you satisfy the conditions that we described previously. So you get pointwise divergence-free velocity fields. And they work very, very nicely, as you can see. So these are smooth splines. These are quadratic splines here. All right, so they'll give you a glimpse of an application of the kind of things that you're really going to get into the detailed mathematics of. It brings in a lot of mathematics that's beautiful mathematics from different areas: differential topology, algebraic topology, differential geometry, and analysis. That will all follow tomorrow and thereafter. So let me summarize with some final thoughts. Isogeometric analysis is one of the most active areas of finite element and computational geometric design research, both from engineering points of view and from mathematics points of view. The overarching goal has been to improve the engineering product design process, and everything has emanated from that. And the focus has been on the design through analysis process, although now many people are looking at manufacturing, additive manufacturing, and other generalizations of this utilizing isogeometric analysis. There are increasing commercial activities. LS-DYNA has isogeometric analysis capabilities available, and they're being extended. Coreform is a startup company that is basically an isogeometric analysis company, modeling and analysis. So the main point, whenever you develop a new technology, an engineering technology, a product, there are really three axes: better, faster, cheaper. You want to get at least one. If you've got two, you probably have a hit. And if you're really greedy, you want to get all three. And I think with isogeometric analysis, in many situations, you can get all three. You can improve the quality of analysis, you can do faster model development and faster solution, and you can decrease cost. So with that, I will finish and thank you for your attention. And since we're still in the pandemic time, I'll put my mask on too. Take it off.
So I would thank you very much for this very I don't know if there is any question in the audience, comment or whatever. I have so.
If you have to raise question, you have to switch on your mic. In case you have problems, you raise a hand. There is a specific feature of Teams to do that. So here is one, Franco e Donatella guest. Wait me just a moment, I allow you, but you should be. Donatella. Okay, here we are. Why isn't it? Okay, Franco and Donatella, you should be able to speak now.
It seems not. I see. Okay, now maybe it's better.
Okay.
Now it is possible now.
Yeah.
Okay. Can you hear me?
Yes.
Okay.
Yes.
Well, hi, Tom.
Hello, Franco.
It was a very, very nice lecture. And well, I have some. Do you know if anybody tried to use those techniques to crack formation or crack propagation?
Yeah, there are quite a few people doing that.
Mm-hmm.
We there are different. There are a lot of different techniques for crack formation and propagation. You have techniques that are sort of like crack capturing. Those are the phase field techniques where you represent the, let's say, the failure through a phase field. And then you have the, let's say, the fitted techniques like XFEM, where you actually insert cracks into the mesh. You essentially put explicit discontinuities into the mesh. So we've even in my group with my collaborators over the years, we've done both, and so it works quite well. I think the accuracy, again, finite elements compared to isogeometric in the phase field area is quite dramatic. When you're putting the discrete cracks in place, it's in both cases, from my point of view, it's a little bit complicated. You can make fast techniques for very simple problems like 2D problems, but once you try to do discrete cracks in three-dimensional problems, the geometry and the topology of the cracking formation becomes almost impossible to model with discrete cracks. Cracks are very, very complicated technology, and they intersect. And so I think for problems like that, the phase field approach is probably the best approach. But in 2D, people use discrete crack methods like XFEM quite a bit, and you have finite element and isogeometric XFEM versions. And I think, again, you can argue the better technology. I just think you have better functions in isogeometric analysis compared with C0 finite elements.
Thank you.
You're welcome.
May I ask another one?
Yeah. Ask me, does Austin, Texas have a soccer team now?
No. This is a very bad period for soccer.
We do, and we won our first game yesterday. In history.
Franco, why bad period for soccer?
Well, for Juventus supporters.
For once.
Now, I remember a certain moment when you say that reaching the max regularity, you had a drop in the cost. So you have a impressive gain passing from P-1 and P. There was a slide like that. Do you remember where?
Yeah, I can get to it very fast. Whoops. Let me. For some reason, my screen has frozen. I can't move my. Let me just. Yeah. Okay. I got out of it. Okay. You see, I had a million slides on structure preserving that I didn't show. But anyway, let's see. This is the one. Oh, Am I
Remember that you had a big improvement when you were passing from P-1 to P. So when you reach the maximum regularity, you have a big gain.
Yeah, I had it on there, but somehow you're not seeing it for some reason.
No.
But
you know, my question was very simple-minded. You possibly can answer easily. But how does the method know that you just, you know, P is the last guy?
How does it know? Well, it knows it through the basis functions, you know. I think we see that in different ways. Let me see if I can just pull it up. This is annoying right now. I have to.
Maybe
just have a blank.
You might stop the sharing and start it again.
No, I mean, it was just a curiosity.
Yeah.
We could check it some other time and you will
it,
explain it to me.
Yeah. Well, that's a good question. I mean, I don't have a good reason. Maybe Espen has a good answer for that, but those are analytical results, and the drop is the improvement is in accuracy per degree of freedom, and it's just the jump is very, very significant. In fact, like, you know, when you go from that case, I'm looking at the picture right now, going from like C-1 for P equals 10 up to continuity CP minus 2, the gap between CP minus 2 or the improvement between CP minus 2 and CP minus 1 continuity is probably greater than the drop in all the previous levels combined.
Yes.
So it's a very salient feature of this stuff. But why that happens, I don't have a good answer. One thing I know, though, is when you do that, you don't have those these, like, say, spurious spectral branches. You know, with the C0 finite elements, you see it very dramatically. But
yes.
if you go to higher splines and you have lower continuity, you see it to some degree too. You know, the worst case is the lowest, but you see it unless you go to the maximal continuity. Now you can control the continuity, of course. You know, at material interfaces and things like that, you drop the continuity down to C0 because that's physically appropriate. But as far as when you're looking at like a homogeneous domain like this, there's just a big gain there. It's enormous.
But does it mean that you are reaching some sort of a spectral method? Well, what does it really mean that you get the maximum continuity?
No, well, maximum means you're still a B-spline. If you ask for one more level of continuity, you have a global polynomial.
Yeah.
So yeah. So
you're going towards the spectral.
Exactly, and you see that in the spectrum. You know, almost the whole spectrum is converging for you. So yeah, and that, you know, brings me back to that remark I made that somehow these K refinement is kind of filling in that space to some degree between, let's say, C0 finite element spaces, which are geometrically very flexible, and spectral methods, which are not.
Yeah. I liked a lot the K refinement.
Yeah. And I think, you know, one needs to look at this as going forward as a basic tool of numerical analysis. Controlling continuity in addition to degree is creating a whole spectrum of tools that previously we just didn't have. We were either spectral or C0, more or less. That was basically it. So there's a lot more here.
Yeah,
it fits what comes out of design. You'd be surprised. You know, many people think, well, the spline codes for design, they're all cubic and stuff like that. we see things that are 8th order, 11th order coming from automobile companies. So people are using very high order spline for CAD.
Don't you get ill conditioning for those high degrees?
Well, that's a good question. We see some conditioning issues if we go very high and have things like very thin structures, like curved shells, and when you get very high order, we found like 8, 9, you start to have severe conditioning issues.
Yeah.
What we've seen those, we can kind of go up to about 7 with no problems, it seems.
Yeah, well, that's already good.
Yeah.
Yeah. And some of the CAD files too, when they're doing like the CAD files for the car body, they want them very high order because they want them to be very smooth. The reason is, one of the uses of CAD is to make the pictures of the cars. So in the advertisements and what you see if you don't have really high quality surfaces is funny reflection patterns, and your eyes pick that up immediately, and that means it's not such a good, So yeah, and one of the things I always find amusing too about CAD is that a lot of the cars you see in magazines and the cars you see on TV and advertisements, they look very realistic, but they're actually CAD files. You think it's a real car because they can put the surroundings in. It looks like a car, but they're really CAD files because the CAD files will look better than the real car.
Well, now I'll shut up. Thank you very much. That was better.
Bye.
Bye Donatella, bye Franco.
No, aspetta, vediamo se c'è. Watson.
There's another question. Let me see who's the one asking. Or maybe it was still...
Now I'm seeing everybody all of a sudden. And now I think I can share my
microphone is working now.
Yeah.
Can you hear me?
Yeah, speak louder.
Yeah. Wonderful talk. Thank you for that. I guess I was interested in the isogeometric method with moving mesh too. So you've talked about this K-refine, and I guess I was interested in coupling that also to moving mesh.
Right. Okay, well, I would say, let me get that again. Let me share my screen. Are you seeing my screen now?
Yeah.
Oh, okay, good. Okay. Well, there's the picture, Franco, from before. Now let's go back down, way down south here, where we had the moving mesh. Okay. So in some sense, this is K-refined. The fluid domain is NURBS, and the wall is NURBS. Everything is moving. That part of the technology is pretty straightforward because this is a boundary fitted mesh, although it's an Ale mesh for the fluids, arbitrary Lagrangian Eulerian. The complication comes from immersing the valve in the Lagrangian description within the moving mesh, the background moving mesh. And the valve is tied to the artery wall on the outside. And I'd say the real complication in the technology is really to have the flow completely stop as the valve completely closes. It has to completely close. If it regurgitates or if there's flow through it, that's no good. You don't want that to happen. So what specifically are you interested in moving meshes and K-refinement? These are all smooth splines. So you could say these are maximally smooth splines. This is all, in a sense, K-refinement, though the order is probably 2 or 3, as I recall.
I guess I was just interested in the state of the art, also from the analysis standpoint in terms of convergence results.
Oh, okay. There's a little bit. There are some things on this. People, well, for immersed methods in general, there's now quite a bit. There's been a lot of work over the years by Baffy and others. Lately, there's been a lot of mathematical papers on so-called cut finite elements and cut IGA. And I would say Mats Larsson and colleagues has published some very nice papers on that. And the nice thing about Mats Larsson's work is that he looks at cut finite elements and cut IGA, so he can compare the mathematical results for both. And again, there seem to be some advantages for splines in his mathematical work. So I think that's the state of the art. Now, when it comes to immersion in a moving domain like this, where you have one moving inside a background moving domain, I don't think there's any mathematical results yet that cover that case, although we did some simple studies of fixing the background mesh and immersing something in it. We call this approach Immersogeometric, and so we've done a little bit of mathematics on it. There's a paper in the Franco's journal, Mathematical Models and Methods in Applied Science, by a number of us that collaborated on that. Yu was, I think, probably the main person involved, and then a cast of many people. Ming-Chen Su, one of the names here, was involved, and David Kamensky. And there's some model problems made up for fluid structure and interaction that were studied mathematically in there. I mean, the problem, one of the problems is you have, like, this is a surface, okay? This is a surface immersed in a volume. And of course, the main problem is the regularity. The regularity is horrific. So you get convergence in rather weak norms, like negative norms, you know. And you see that in practice. And then you find, well, there are ways of really improving things. But if you do things in sort of a straightforward way, the results can be pretty ragged, even though you're converging in some very weak negative norm, you know.
Yeah, thank you very much.
Yeah.
As far as I see, there seem to be no further questions. So what about you, Carla?
No, me neither. So I think that we can thank Tom and all the participants and the attendants for this talk. It was really interesting. It was a pleasure and really impressive. So thank you, everybody, and goodbye. Thank you, Tom.
Thank you, Carla.
Thank you. Thank you very much.
Okay. I guess I'll sign off. Thank you.
Goodbye.
Goodbye. Thank you.
Thank you. Bye. Goodbye. Thanks for organizing this.
Thank you for attending. Ciao Giancarlo, ti abbiamo visto adesso.
Ciao.
Ti ho visto ora.
Thank you and goodbye.
Ciao,
Ciao
ciao.
Giancarlo.
Ciao Carla.
Ciao.
Ciao. Ciao a tutti.
Va bene. Adesso vado. Cosa faccio? Ok.
Ah, c'è anche. Ok, so tutto a posto Fabio, sì?
Sì, tutto a posto.
Benissimo.
Allora,
Grazie.
quando è pronta la metto sul sito.
Grazie mille.
Figurati.
Grazie mille.
Bene. Ciao, ciao.
Grazie. Ciao.